This video is about the pitch dynamics of a vehicle and hence about anti-dive and anti-squat suspension geometry. Due to inertial forces and the vertical elasticity of the suspensions, a vehicle performs a pitching motion during acceleration and braking. In particular, the acceleration of the vehicle causes a positive pitching motion, mainly because the rear suspensions are compressed. This type of motion of the vehicle is also called a squat. For the braking process, it's just the opposite, so the vehicle performs a negative pitching motion by compressing the front suspensions. This type of motion is also called a dive. As you can guess from the name, anti-dive and anti-squat geometry is about how to design the suspension geometry in order to reduce the dive and squat motion during braking and acceleration respectively. Note that anti-dive and anti-squat has almost no effect on the weight distribution of the car, which was discussed in our video on acceleration and braking performance. The reason is that pitch angles are typically very small, and hence the location of the center of gravity is almost unchanged by a pitching motion of the vehicle. Instead, what the anti-dive and anti-squat suspension geometry really changes is how much of the vertical tire forces really pass through the springs versus the links or control arms of the suspension. Since the links and control arms are essentially rigid, the more of the vertical forces that pass through them instead of the springs, the smaller will be the compression of the corresponding suspensions. In order to get a better understanding of how all of this actually works, we need to take a look at the concept of virtual pivot points. To this end, we will need the insights into the longitudinal dynamics and the suspension kinematics from the previous videos. In the first step, we consider the kinematics of a suspension, solid axle suspension or independent suspension, from a sidewards perspective onto the vehicle. Assume for a moment that the vehicle chassis has a fixed position and fixed orientation in space. Then there must exist an instantaneous center of rotation for the relative motion of the wheel with respect to the chassis. If the relative motion of the wheel with respect to the chassis is just of a translatory nature, then this center of rotation will be at infinity. However, actual suspensions are deliberately not designed like this, so in reality, the instantaneous center of rotation is a finite point that can be considered as the virtual pivot point for the wheel about the chassis. Hence, it shall be called the virtual pivot point. For some suspensions with very specific kinematics, it is possible to determine the location of this virtual pivot point very accurately. For example, let's look at the double wishbone suspension, which is fixed to the vehicle chassis at these 4 points. Since the upper wishbone is a rigid body that rotates with respect to the chassis around this axis, this means that also the fixing point of the hub carrier to the upper wishbone rotates about the yellow axis when the wheel moves up and down. Looking at this schematically from a sidewards perspective, the yellow axis is aligned with the upper control arm. We already know that this fixing point up here has a velocity vector that's perpendicular to the yellow axis, and hence this pivot point has to lie somewhere on the dashed axis. The same argument applies to the lower wishbone, which rotates around this axis about the vehicle chassis. Hence, from a sideways perspective, the fixing point of the hub carrier to the lower wishbone must have a relative velocity that's perpendicular to the rotation axis of the lower wishbone. By the same argument as before, the center of relative rotation of the hub carrier about the vehicle chassis has to lie on the line that's perpendicular to that relative velocity, so the dashed axis. Now, since the pivot point has to lie on both dashed axes, it has to be equal to the intersection point of these two axes. For another example, let's look at the Mcpherson strut suspension. The lower control arm of the suspension is of course equivalent to the lower wishbone of the double wishbone suspension. In other words, it is fixed to the vehicle chassis in these 2 points and can rotate relative to the chassis about this axis. Again, looking at the suspension qualitatively from a sideways perspective, the yellow axis is aligned with the orientation of the lower control arm. Hence, the lower fixing point of the wheel hub to the control arm must have a relative velocity that's perpendicular to the yellow axis. The second relative velocity vector has to come from the Mcpherson strut. Note that it's fixed to the vehicle chassis by something similar to a ball joint. In other words, the rigid body made up of the strut and the wheel hub can perform a translatory motion in this direction and a rotatory motion around the ball joint. However, the ball joint is fixed to the vehicle chassis, so at this point the relative velocity can only go in the direction of the strut itself. Therefore, the virtual pivot point that we're trying to construct has to lie on an axis that's perpendicular to this relative velocity vector. So now the virtual pivot point has to lie on both dashed axes, and hence it has to be equal to their intersection point. Now, a few remarks about the construction of the virtual pivot point. We've only seen the construction of the virtual pivot point for 2 examples, namely the double wishbone suspension and the Mcpherson strut suspension. However, a virtual pivot point exists for all types of independent and solid axle suspensions. Nonetheless, the precise location of the virtual pivot point is generally not known. Every kinematic construction, like the ones we've seen above, are only a more or less accurate approximation of the true virtual pivot point. And finally, for some suspensions, the location of the virtual pivot point is more accurately predictable, or as we say, the virtual pivot point is kinematically more well defined than for others. Of course, the 2 examples above have been chosen such that the virtual pivot point is very well defined. Practically speaking, this is considered a big advantage of a suspension if the virtual pivot point is well defined. And that's because it gives the designer of the suspension good control over the actual position of the virtual pivot point. And why the location of the virtual pivot point is important will be our next subject. So let's finally turn to the question of how the virtual pivot points of the front and rear suspension relate to the anti-dive and anti-squat of the vehicle. We begin with the case of acceleration and consider a rear-wheel drive vehicle. The center of gravity of the vehicle and the virtual pivot point of the rear suspension are given and shown in purple and yellow here respectively. In the following, we will not consider the static forces such as the weight of the vehicle that attacks in its center of gravity and that's compensated for by vertical tire forces at the rear and the front tire. Instead, only those forces associated with a deviation from the static equilibrium will be considered in the following. The first deviation is clearly the longitudinal tire force Fx acting on the rear tire. It causes an inertial force equal to the mass times the longitudinal acceleration, which acts in the vehicle's center of gravity and points in the opposite direction of Fx. And of course, it has the same magnitude as Fx. The moment caused by this parallel pair of forces will be compensated by a difference in the vertical tire forces at the rear and the front tires. To see this, let's take a balance of moments about the contact point between the front tire and the road. This yields delta FCR times the distance L minus Fx times the distance h equals to 0. And therefore, delta FCR, the additional vertical tire force at the rear tires, equals to h divided by L, where h is the height of the center of gravity and L is the wheelbase of the vehicle, times the longitudinal tire force Fx. So what this tells us is that there's always a fixed ratio between the longitudinal tire force and the additional vertical tire force that's incurred by the longitudinal tire force. Hence, the resulting force of Fx and delta FCR, shown in purple here, always points along the same direction, and that direction is defined by the ratio of h over L. So it's shown as the dashed white line here. Now, under what condition will we see a squat of the rear suspension? The answer is we will see a squat of the rear suspension if the resulting force, shown in purple here, has a moment about the virtual pivot point. So, in particular, if the virtual pivot point happens to lie on this white dashed line, then the resulting force will have no moment about the virtual pivot point, and hence there will be no squat of the rear suspension. However, the farther the virtual pivot point lies below the white dashed line, the higher will be the moment of the purple force with respect to the virtual pivot point, and hence the more will be the squat of the rear suspension. This can be expressed more formally by a balance of moments about the virtual pivot point. In fact, the total additional moment about the virtual pivot point compared with the static case is given by delta FCR times the distance d minus Fx times the distance e, where d and e represent the longitudinal and vertical position of the virtual pivot point with respect to the rear tire road contact point, respectively. Substituting delta FCR from this formula, we obtain this expression for the moment about the virtual pivot point. From this formula, we can see that 100% anti-squat is achieved if the ratio of E and D equals to the ratio of H and L, meaning that the virtual pivot point lies on the white dashed line. We say that X% anti-squat is achieved if the ratio of E and D equals to X divided by 100 times the ratio of H and L. A very similar case can be made for the situation of braking, only now we consider the virtual pivot point of the front suspension. We use the Greek letter xi to denote the fraction of the brake force that's developed at the front axle. In other words, the tire force at the front axle Fx is equal to xi times the total brake force F brake. The rest of the braking force, namely 1 minus xi F brake, is applied to the rear wheel, so that the total inertial force that acts on the center of gravity of the vehicle equals 2 minus m times a ln, where a ln is the negative longitudinal acceleration, and this is equal to the total braking force of the vehicle. Since these three parallel forces act on the vehicle along different lines, they will cause a moment on the vehicle, which is compensated, of course, by vertical tire forces. Taking a balance of moments about the rear tire road contact point B yields the following equation: minus delta FCF times the distance L plus F brake times the distance h equals to 0. And therefore it follows that delta FCF equals to h divided by L times F brake. The balance of moments of the front wheel and suspension about its virtual pivot point reads as follows. The total moment MVPP that's responsible for compressing the suspension is equal to delta FCF times the distance d minus xi times F brake times the distance e, which, by substituting this expression for delta FCF into here, yields this equation, so that the total moment can be expressed as the ratio of h and xi L minus the ratio of e and d times xi F brake d. What this means is that the locus of virtual pivot points that achieve a zero compression of the front suspension during braking is given by this dashed line, whose slope is defined as the ratio between the distances h and xi L, and which starts at the contact point of the front tire and the road. We conclude that 100% anti-dive can be achieved if the ratio of E and D equals to the ratio of H and xi L, and we say that X% anti-dive is achieved if the ratio of E and D equals to X divided by 100 times the ratio of H and xi L. Let's conclude this video by some practical remarks about anti-dive and anti-squat. First, 100% anti-dive and 100% anti-squat are rarely used in practice, even though this would be technically possible. The reason is that some degree of pitch rotation during braking or acceleration improves the driving feel. Typical values for anti-dive and anti-squat are between 60 and 80%. And finally, we have to keep in mind that the design of the anti-dive and anti-squat cannot be considered independently of other dynamic properties or performance measures of the vehicle. And some of them we'll get to know in the next few videos.